Exponential growth and geometric sequences. You should be familiar with sequences of numbers, and it may be helpful to understand the commonly used notation. It is also helpful to understand linear growth and arithmetic sequences, which are based on an additive pattern. This lesson is similar, except that we will use multiplication at each step instead of addition. In this lesson, we will define geometric sequences, both explicitly and recursively, and find both explicit and recursive formulas from the sequence of numbers. Exponential growth occurs when a quantity increases in size through multiplication. The simplest example is something that doubles each step. Suppose you have a soybean field infected with a certain type of insect pest, and each day the infected parcel of land doubles in size. The infestation has doubled after one day, then doubles again, and again, and again. This process continues until the entire field is contaminated. The notation used is similar to the notation for arithmetic sequences, except that this time in the recursive part of the definition we are multiplying instead of adding. In this sequence, we can see that we get from one term to the next by multiplying by 10. Writing the sequence from the definition requires that we know an initial term, in this case 5, and then getting the next term by taking the previous term and multiplying by 10. The explicit formula will require us to count the repeated multiplication with an exponent. To get the first term, we plug the value 1 in for n to get 16 times 1/2, which is 8. If you prefer, you could start with the initial term g sub 0. Let's go in the other direction. Given the sequence, find the formulas, both recursive and explicit. The recursive form is easier to find. Recall you must give two pieces of information in a recursive definition. You must specify the initial term, in this case g sub 1 equals 12. You must also specify how to get from one term to the next. For a geometric sequence, the recursion will be multiplying, so we need to find the common ratio. We can take any two consecutive terms and divide. In this case, we see each term is 4 times the previous term, so the recursive step will be to multiply by 4. Specifically, g sub 1 equals 12, and the next term, g sub n plus 1, equals 4 times g sub n. To find the explicit formula, it is again helpful to find the value prior to the first term. If we divide once more by 4, we get g sub 0 equals 3. This allows us to have already performed one multiplication for the first term. The explicit formula will begin with 3, then count the number of times we multiply by 4 in the exponent. The explicit formula is g sub n equals the initial term of 3 times 4 to the nth power. Let's find formulas for this geometric sequence. G sub 3 equals 2 and g sub 7 equals 162. 162 divided by 2 is 81, so we accomplish a multiplication by 81 in 4 steps. In order to find the common ratio, we need to find a number we can multiply by itself 4 times to get 81. In other words, we need to find the fourth root of 81, which is 3. The common symbol for the common ratio is the letter r. Now that we have the common ratio, we can start filling in other terms, beginning at 2 and multiplying by 3 each step to the right. We can divide by 3 as we go to the left. G sub 1 is 2/9. For the explicit formula, we may wish to find g sub 0, which is 2/27. The recursive definition gives the initial term g sub 1 equals 2/9, and the recursion where the next term is the previous term times the common ratio of 3. The explicit formula starts at 2/27 and then counts the number of steps, which is the number of times we multiply by 3, which is the exponent on 3. Here is another example of a geometric sequence, the application of compounding interest. You put a $500 purchase on your credit card, and at the end of 9 months, you owe $571.70. What is the interest rate? This can be thought of as a geometric sequence with the initial term g sub 0 equal to 500 and the ninth term 571.70, one term for each month. We get to each month by multiplying by the common ratio. After multiplying 9 times, your loan has increased by a factor of 1.1434. Taking the ninth root of 1.1434, we find the common ratio of 1.015. The 1 in the multiplying factor tells us that you still owe the initial $500. The number after the decimal implies that the interest rate is 1.5% per month, or 18% annually. To recap, geometric sequences rely on repeated multiplication. The recursive definition specifies an initial value and a recursion, which determines the next term by multiplying the previous term by the common ratio. The explicit definition multiplies g sub 0 by the common ratio once for each step, so the number of steps is the exponent.